Hi, welcome to Advanced Strategy and Analytics. This is lecture 3 of our course, and we are going to be going over everything related to data and analytics. Going through the agenda for today, we'll first start about data types, simply going over how we measure data in the world. Then we'll be getting into data engineering and the process that we go through with data. Then we'll be going into statistics, and then we'll be diving into machine learning. We use data to measure qualities in our world. Now, we live in a world of qualities, not quantities. The world is analog and continuous. However, for us to better make sense of the world, it helps us to break things down into quantities so that we can measure the world, so we can have some sense of orienting ourselves within it. Now, there are two major variable types. There is categorical variables and there's quantitative variables. These are really the main variable types that you'll need to know and work with. The main difference between categorical variables and quantitative variables is categorical variables, just think of anything. If it's a quantity, if it's a category, then it's probably a categorical variable, where if it's some kind of number representation, then it's a quantitative variable. But going through the different types of categorical variables, we'll first start out with the discrete variables, and just really quickly going beyond explaining the difference between discrete and continuous. Discrete means that there is a definite stop between two variables. One way to think about this is like people, for instance. You either have one person or you have two people. You can't have a person and a half. Where continuous means that there's an infinite scale between something. You think of like size measurements. You can't have 1 inch and you can't have 2 inches, but you could also have 1.5 inches. And even if you have 1.5 inches, there's still an infinite scale of inches you can have between between those two numbers. And that's the main difference between discrete variables and continuous variables. Going on into the first type of categorical variable is nominal variables. These are variables that you really can't order. Just think about it as a category. There's really no sense of hierarchy in it. Common examples could be gender, names, or colors. One gender is not necessarily ordered over another gender, or you can't say that, say, red is greater than blue. They're just two different categories that you can put something in. After nominal data, and nominal data is the most common type of categorical variable you will most likely encounter. Then you have ordinal data. Now, ordinal data gets tricky, and a lot of people like to think that ordinal data is quantitative, but it's not quantitative because with ordinal data, you can't actually extract measurements from it. For instance, the most common example of ordinal data is ranking. Um, like say you have a marathon going on and somebody gets first place and the second person, and then you have somebody that gets second place and somebody that gets third place. Each of those rankings would be considered ordinal data because first place is greater than second place and second place is greater than third place. But you can't actually say anything. You can't say, for instance, that the person in first place was 3 times as fast as the person in second place because there's no measurement between it. All you know is that first place was ahead of second place, but you don't know if second place was, say, 1 second behind first place or if they were an hour behind first place. And because of that, ordinal data is not quantitative, it's categorical. However, I will say in business use cases, when ordinal data is all you can get, sometimes it might be used as quantitative in quantitative analysis. Statistically, this is incorrect. In the real world, though, you might have some cases, though, where you do have to, that's all the data you have to work with, and you have to go with that. But just be aware, if you are using ordinal data to do quantitative analysis, be aware of the shortcomings that it has. Okay, moving on into quantitative variables, we have count. Now, count just represents the number of something, and it has to be whole numbers. You're not going back to the people example. If you're counting the number of people that you have, you can't have a half person. It has to represent the numbers of objects, or it can represent the frequency of events. Okay, now moving on into continuous data. Um, this is most often what you see and what you use for quantitative of data. We'll start out with interval data. Now, interval data, what makes interval data unique is there's no true zero, but everything is evenly spaced. A common example of this is temperature. For instance, you can say if you're comparing, say, Fahrenheit and Celsius. Now, there is an interval quantity between different degrees of, there is interval quantity between different degrees of a temperature. However, you can't say that if it's that say 70, 80 degrees Fahrenheit is twice as much as 40 degrees Fahrenheit because there is no true zero for that, so you can't actually describe it being twice as hot. Because if you swap over to a Celsius scale, it's completely different. So another example of interval data is also test scores. You can't say somebody is twice as smart as somebody else. If somebody scores 100% on a test and somebody else scored 50% on a test, you can't say that the person that scored 100% is twice as smart as the person that scored, say, 50% on the test. But you could say that um, there is a measurable distance if you have a person that scored 100%, a person that scored 75%, and a person that scored 50%. You can quantize the difference of their performance by 25%. And then finally, the last type of quantitative data is ratio data. Now, ratio data is different from interval data in the fact that it does have a true zero. And usually interval data is a little bit more abstract, where ratio data is a little bit more concrete. Think about something like length or weight. For instance, you can definitively say that 4 inches is twice as long as 2 inches, and there is a continuous measurement between that. Okay, I know that all of these data types, it's pretty rudimentary and fundamental. However, it is good just to be aware of it, especially moving forward. Really, all you need to know, I would say, is being able to differentiate a variable between whether if it's categorical or quantitative. Next, it's also important to understand when trying to figure out the relationship between two variables, you need to understand which variable you are looking at as the variable that causes another variable and being able to differentiate those two variable types. For usually when you're trying to describe a relationship between two variables, you will look at a single dependent variable that you are interested in changing. And then you will look at that dependent variable's relationship with a single or multiple independent variables that affect that dependent variable. I know this is super simple, but it is and super fundamental, but it still is important to be able to differentiate which variable um, is your target variable, the one that you your outcome variable, and also to be able to identify what your inputs are. Typically, your dependent variable is the variable you do not have control over, where your independent variable are variables you have control over. And the idea is you want to figure out how you can manipulate your independent variables to get the desired outcome of your dependent variables. Also, I want to list out that these variables have many, many different names and they're all used interchangeably. Um, so I'd recommend just giving a quick look over these different variable names just to be able to identify and know what something when somebody says one of these variable names, know what they're referring to. Okay, so next we'll be getting into data engineering. Now, a really quick brief overview of what data engineering is. It is the idea about now we know how to measure um, qualities within the world. The whole idea of data engineering is now how do we store that information? How do we process it and put it in a position to make it useful? So starting with data storage. There are two main ways that data is commonly stored. You'll find that data is either stored in a table or in key value pairs. Now, a table, we'll start off with this. Tables are probably what most people are most familiar with. Tables date way back to the Babylonians. They were used before writing was even established, and this was a simple way to be able to store data. So the way a table works is you'll have columns and rows. In columns, each column will represent a feature of, of the data, where each row will represent an observation. You can think as features as a characteristic. For instance, like if we were looking at students, we'd have each student would be represented as an observation, and then the different features of a student we could describe maybe what's their name, what class are they in, what's their grade standing, and so on. And then we'd give values for each student for each of the different features that they have. A key value pairs is a little bit similar. However, it's a little bit more flexible, and this is used if you have a background with programming. You're probably familiar with key value pairs structure and storing data. The whole idea behind key value pairs is that I will have a key, and then when I access that key, it will return to me data that I want. And so you can think about it in terms of, let's say that using that same student example, I might have um, I might have a student as one of my keys. So when I call that student as a key, it will return to me all these different values. And I can also have keys and values within keys and values. So say like I want to get a student's class list. So I'd call the key for that student, and then within the key, I would call the key for their classes. And then when I call that, that would return to me a list of all the classes that a student is in. What's nice about key value pairs is if we wanted to perform that same kind of operation over here on a table, now I can't just say student one. If I said student one in classes, I can't just return a list of all the classes. I'd have to make a feature class one, class two, class three, class class 7. And where this gets tricky is some students have variable numbers of classes. Some students might have a lot of classes where other students have very few. So I'd have class 1, class 2, class 3, for the different students. However, one student might only be taking one class, so I'd have to leave class 2 and class 3 blank for that student, which is a waste of space on the table. Where if I did it with a key value pair structure, what's nice is I don't even, maybe a student isn't even taking classes that semester and I don't even have to have that feature for that student. So really quickly going over the pros and cons of each, we'll start with a table. Tables are great because they are very easy to understand. Most people are very familiar using tables. And most importantly, tables are very easy to manipulate and to perform data analysis on. The cons for it though is tables are not very flexible because like we were talking about with the student example, you have to have data structured in a format where everything is consistent together. In addition, tables can be slow to retrieve and get information from, or to put and also to put information in. Key value pairs, on the other hand, the pros to them is they're very flexible. As you saw, we can accommodate for different features of we can accommodate for different features unique to different characteristics. They're also very fast to put data into. I won't get too much into it, but oftentimes key value pairs use hash tables, which makes them a lot faster as well for getting data from. However, one of the biggest cons for key value pairs is they're extremely hard to do, not extremely, but just they're a lot more difficult to do data analysis on or to analyze. Usually when you get a file back in a key value pair format, you will have to change this data structure to a table structure before you can actually do any analysis on it. So just keep that in mind. One structure is not necessarily better than the other structure. It's just important to know the use cases for the different structures, what you're trying to do, and knowing when to use them. There are many more different types of structures out there, but these are the two most common that you'll probably be working with the most. Now, here is a much more exhaustive list of all the different ways how to structure data. And you don't need to be familiar with every single one of these. However, it is good to know the different options that are out there. And I want to give you a general sense of the difference between structured, semi-structured, and unstructured data, just in a way that is easy for you to understand. So I'm going to compare storing data to putting away laundry. Now, I have different options for the way that I can put away my laundry. Now, one option, I could take a structured approach in putting away my laundry, where I will open up my drawer, I'm going to fold all my clothes, and then I'm going to section out my clothes in specific ways so I have different clothes all grouped together. For instance, I'm going to have my pants on one side, my shirts on another side, my athletic clothes on another side, so it's very easy for me to find it. I am going to match all my socks together and fold them together, and I'm going to put all of those into different drawers. Now, this takes a while for me to do my laundry this way because I have to index it. I have to figure out a structure for how to put it in. But the advantages of me of putting away my clothes like this is it's very quickly for me to take my clothes out when I need them. When I need to find pants or socks or athletic clothes, I can know exactly where to go for that. Now, using that same, continuing this metaphor, going into a semi-structured approach. Now, when putting away my clothes, if I want to take a semi-structured approach, maybe I'll just have a drawer for my pants, a drawer for my socks, a drawer for my shirts, However, I don't fold my clothes. I just throw my clothes. I'll just throw all my shirts in one drawer. I'll just throw all my pants in one drawer, and then I'll just throw all my socks in another drawer. I don't have them organized at all, but they're just there. And what's really nice about this is it saves a lot of time. It's a lot faster for me to put my hey for my to put my clothes away. And also what's it's also more inflexible for me to put away my clothes away like this. Say like if I find a sock, I do not have to spend the time trying to find the other sock. I can just throw a single sock into my sock drawer and not worry about trying to find its pair. However, when I go to take my clothes out, I will have to find that second pair at the time that I'm retrieving that sock. There is still a structured approach though to putting away my clothes. I do have specific drawers so I know kind of where to go when I want to get my clothes. And this is great if I don't really care about what I wear every day. If I know, oh, I just need to wear a shirt and pants, then I just open the drawer. I don't have to really differentiate all my clothes. I'll just take whatever I find there and take it out. So, but one of the disadvantages is that it's a little bit longer for me to find whatever clothes I want to get. And finally, I can take an unstructured approach at putting away my clothes. Now, an unstructured approach to putting away my clothes would be I just throw them all into a pile. I have a pile of clothes that I leave in in one area of my room, and I just put my clothes there. Maybe I will be a little bit structured about it and I'll have multiple different piles, but I just dump all my clothes there. And this is great because it's super fast. I don't have to worry about folding or like putting things away. I just put my clothes wherever I want them to go. However, this can get very messy and it can take forever if I want to find a file or if I want to find um, a specific article of clothing. So I might be digging around for a long time to find something specific. So the general idea is that you are going to pay some kind of cost for finding what you want. You can either pay that cost upfront and how you index something, how you index a an article of clothing, or you can pay that cost afterwards, where you have to pay that cost for finding a specific article of clothing. I know this is a very broad um, oversimplification of how data storage works, but it's an easy way to remember how the different storage formats work. So we have over here structured storage, which is also known as SQL storage. This is usually in tabular form. You can either have a transactional database that is really good for preserving the integrity of your data, or moving over here analytical databases, which are more optimized for handling large queries to be able to figure things out. These are great when you have established schemas or you know what the structure of your data is, and good for doing analytics. Now going into the semi-structured types of data, this is really good, especially I would recommend if you're starting out with a company, you're not sure what your data schema is. This is a very flexible way that you can store data. You have your key value pairs, which we talked about in the previous slide, where you have a key that's attached to receiving certain data. You have wide column form data, which is basically instead of observations being as rows, you have your observations as columns. Then there's graph databases, which you have different nodes, and the nodes are connected to each other by some kind of relationship. And then document databases, which are also known as nested object databases, where you'll have a document within a document, a little bit similar to key value pairs, but more focused on objects. And finally, unstructured data, also known as blob data. This you all are very familiar with this. Whenever you throw a file into whenever you into a folder on your computer, you are essentially dealing with unstructured data. Now, here are just some of the services that all go with these different types of data formats. Like I said, you don't need to know this. You don't really need to know everything on this slide, but it's just good to be aware of. If you ever perform any type of analysis on data, you will go through this process. You'll first start off by storing your data somewhere. Then you will perform the necessary calculations or transformations and cleaning on the data. And then finally, you will display the data in some type of format. So this process is also known as the ETL process, which stands for extract, transform, and load. You extract your data from a storage, from some kind of storage area. Then you are going to transform your data, and then you're going to load it into some kind of staging and displaying environment. Um, this process is pretty straightforward, and you always naturally go through this process whenever you're doing any kind of data analysis. However, it is good to understand the different elements of this process because when you start to scale, whenever you need to do any type of data analysis, whether it's very small for just like a single quick inquiry from your boss, or if you're trying to build an entire machine learning model for an enterprise application, you need to understand kind of what the tools, where you're going to have to go to get the data, to process the data and display it, what kind of tools you need, and what the process is going to look like. So I just want to run through some examples, starting out from very simple, then moving on to more complicated. So I'll start with a single file example. Let's say that my boss wants me to do a quick analysis on some data, on a data inquiry that he has. So I get an Excel file. And I need to then extract some kind of insights from that Excel file. What I'll do is I'll take the Excel file that she gave me, I'll take the sheet, and then I'll highlight that sheet and I'll use that sheet as my data source. I will then put that sheet into a pivot table. I'm extracting the data from the pivot table, from the sheet into a pivot table, and then I'm using the pivot table to transform and manipulate the data to get it in a format that I want it to be in. And then once that I'm done with my pivot table calculations, I'll then load that into an Excel graph that then displays the output of my analysis. So the Excel graph references the pivot table, and then the pivot table references the Excel sheet. That way, if I update something on the Excel sheet, it will automatically update on the pivot table and thus update on the Excel graph. That is a very common process that a lot of people, or even almost anyone in business analytics, has done at some point. Now, moving on to a little bit more complicated example, I might be working on a case. The case has a lot of data that we are getting from a client, and we want to establish a pipeline for being able to quickly perform the same routine analysis on that data. So that client is constantly giving us CSV files, and we want to be able to perform the same analysis on those CSV files that the client is giving us, but we don't want to have to go through and manually do it in Excel. So what we might do is we'll have a location where the CSV files are sent. Then we'll hook that up to an Alteryx flow. Alteryx is a program that does simple data analysis locally. They might also be able to do it in the cloud, but in all the circumstances that I've used Alteryx. It's mostly just been for um, local data manipulation. What I'll do is I'll open up Alteryx and then I'll reference the CSV file's location, and that will pull in data from the CSV file. I'll create an Alteryx flow that then manipulates the data, does any of the cleaning, transformations, or whatever I need for it to do, any calculations. Then I'll probably export another, from that, the Alteryx flow will export a CSV file that I'll then hook up to Tableau Desktop, and Tableau Desktop will reference that output CSV file that will then display a dashboard of the analysis that was done in Alteryx. So that's a little bit more complicated process, a little bit more complicated example of the process. And finally, we can go to the most complicated, which would be a full-fledged cloud application or enterprise application, where I would have a SQL server that would store all my customer data or my organizational performance. I would all store that within a SQL database. I would then have maybe an EC2, or if the calculations were simple enough and would take less than 15 minutes to run, probably I'd use Lambda functions that would run Python scripts that would reference the SQL server. They would run SQL queries to extract data from the SQL server. Then in my Python environment, I would then perform the necessary data cleaning, calculations, and so forth to do my analysis, load that into a staging environment that would connect to SAP Analytics Cloud, that would then take my analysis that I done and display it in graph and chart format for executives of the company to see. So you can see whether you're dealing with a simple Excel sheet or if you're dealing with a full-fledged enterprise application, the process for gaining insights from data is the exact same. And it's important when you are doing the pre-work to perform your data analysis to figure out what this process is, to figure out where your data is coming from, how you are going to manipulate the data, and then how it is going to be displayed. Lastly, the last part of data engineering, when extracting insights from data, it's important to understand what type of insights you are looking to extract. And there's two main different types of insights or methods of getting insights that you can get. You can take a statistical approach or a machine learning approach. Now, the biggest difference between statistics and machine learning is that statistics is focused on knowing the relationship between different variables. It doesn't really care about predicting, rather it wants to know or explain why something happens. That is the main goal of statistics. Machine learning, on the other hand, does not care at all about explaining. Rather, it leaves everything to a black box. The biggest focus of machine learning is to create a model that can most accurately predict or produce outcomes. And that's what you have to ask yourself, whether when you're faced with taking a statistical approach or a machine learning approach, is am I looking to explain the causality between variables? If that's important, then I need to focus more on taking a statistical approach. Whereas, am I focusing on making the most accurate model possible, then I would take more of a machine learning approach. However, it's important to understand that both approaches use the exact same basic algorithms, and there really is gray area between the two. But that is the best way I could describe the difference between statistics and machine learning. It really all comes down to what are you trying to get out of the model, whether you're trying to explain something versus if you're just trying to make accurate predictions. Okay, now we'll be getting into statistics, and we'll be going over basic univariate analysis, bivariate analysis, and multivariate analysis. So the type of analysis you'll be using is really determined by how many variables you have. If you have one variable that you're looking at, you'll be using univariate analysis. If you have two variables, you'll be using bivariate analysis. And if you have more than two, you'll be using multivariate analysis. Usually, univariate analysis is most focused on determining the spread or shape of a distribution, where bivariate analysis is most commonly used to really home in on and discover the relationship between two variables, where multivariable analysis is usually they're focused on explaining multiple relationships between variables, where either or they're looking at trying to explain a single variable based on many different variables, or they're looking at how multiple variables in a data set all confound with each other. Univariate analysis draws insights about a single dependent variable by how it is distributed over a range of values. The two most common different ways to display univariate analysis is either with a histogram or with a box plot. With a histogram, you'll have your different ranges of response and then the frequencies of those responses as they appear. Boxplot does the exact same thing, only it's a little bit faster to summarize. It's a little bit more visually faster to summarize. It will show you where the maximum is and the minimum, and then it gives you the shape of the distribution by showing you where the first and third quartiles are, where the medium of the distribution is, and then where the mean of the distribution is. There's three different types of measurements that you usually look at when doing univariate analysis. You look at the center, the shape, and the spread. So the center is kind of where all the data falls. There's three different ways how to look at the center. There's the mean, medium, and mode. The mean will perfectly split the data and will balance the data in half. Whereas the medium is where or is whatever number is perfectly in the center, where the mode is whatever number or whatever value appears the most frequently. As far as shape goes, there's different types of shapes. There's unimodal, bimodal, and multimodal model. This basically means how many hills do you have in a distribution, or how many mountains do you have, and then this gets into skewiness. If the shape is if it is well distributed, if it doesn't have any skewness, then the mean and medium should line up. The farther that the mean and medium are apart, the more it is skewed. If a distribution is left skewed, it would look something like this. I know this can be confusing because the hill is on the right, but one of the ways I like to think about it is you think that you just move the camera over to the left, so then the hill moves to the right. So that's what a left skewed distribution would look like, and then a right skewed distribution would look something like this, where you have all the data is most of the weight of the data is on this side. So again, with the right skew, the camera moves to the right, and when the camera moves to the right, then the hill moves to the left. So that is skewness and for shape. And finally, with spread, you have two different main metrics for determining spread. You have the range, which is the difference between the maximum and the minimum, and then the standard deviation, which is just a metric for how everything is spread out. Standard deviation will tell you what the variance of the distribution is. Next, we have bivariate analysis. And I'll just say right off the bat, you will probably use what is on the slide the most in your careers if you're doing analytics. If there's one slide that I would recommend you take a picture of, it would be this slide. This slide is essentially a cheat sheet for most of the different problems that you'll have. And bivariate analysis attempts to explain the effect between an input variable and an output variable. And so it's important to identify, be able to determine what variable is your input, what variable is your output, and then determine if that variable is a categorical or a quantitative variable, and if your output variable is a quantitative variable or a categorical variable. By doing this, this will determine what type of analysis you will need to perform. This is a very important skill for taking a real world problem and then being able to convert it into a something that you can solve with a statistical approach. For instance, if you have a problem where the input variable is quantitative and the output variable is quantitative, you know that you're probably going to need to do some kind of regression analysis on it. When choosing charts, you're probably going to do some kind of scatter plot or line plot to be able to demonstrate the relationship between it. If, however, your input variable is a categorical variable and your output is a quantitative variable, then you're going to need to perform an ANOVA on it, or an analysis of variance. You're also probably going to end up using a bar chart or a box plot to be able to display the relationship between the two. If you have a quantitative variable as your input and a categorical variable as your output, say you are going to probably need to use a logistical regression or some kind of discriminant analysis to be able to figure out the relationship between the two. And you're probably going to use either a logistics curve or support vector chart. Now I have up here a logistics curve. If you're unfamiliar with a support vector chart, think of this exact same chart, but rather than drawing this dotted sigmoid function that goes through all the data points, instead I would just draw a line right here. And this line would classify these data point, anything below the line would classify these data points as one category, and anything above the line would classify these data points as another category. And then finally, if you're doing a categorical to categorical analysis, if your input variable was categorical and your output variable was categorical as well, then you'd know you'd need to choose some kind of chi-squared test or do perform cross tabulation on it. And common ways to be able to display categorical to categorical tables, categorical to categorical relationships is through a table. Usually tables aren't the best just because they can get hard to read. Heat maps are a great way how to make tables even better because they add instant color to the values within tables. But if you can pull off a Mary-Mechos are great because they actually give area um, rather than just color to who your data to your graph, and also free up color to be used as another dimension. Now there are three measurements usually associated with bivariate analysis. I know they're called different things for each of the different types of analysis, and you can dive much deeper into it. But here's just a general overview of the three different measurements for bivariate analysis. You have number one, strength, number two, variance, and number three, significance. Now, number one, strength. Strength is basically describing the effect of one on the input variable on the output variable. For instance, if your input variable increases by 1%, then your output variable would increase by X%. That is a statement of strength. Going on into variance. Variance is concerned with explaining how much of the model, how well the model describes the data, or how much of the variance can be captured in from the model. For instance, here you see that we have this scatter plot. We have this line, this regression line that runs through the scatter plot. If all of these dots fell on the line, that meant our model would be able to account for all of the variance within the data. So the ability of this line to be able to get as basically the distance between these dots and where the line of our model is, that is what variance tries to describe. And that's usually done in the form of an R squared. Finally, significance. Now, significance is a little bit tricky to understand, but what it's saying is if there is no, assuming that there was no actual relationship between um, our two variables, it measures how likely we would get results as extreme as the ones that we see. I know that's a little bit hard to understand, so I'm going to try to break it down with an example. Let's say that I was doing a test of I made a hypothesis that my penny I have a quarter, and my hypothesis is the quarter only lands on heads. Now, the null hypothesis or is that the coin is completely normal. It will land on heads 50% of the time, or it will land on tails 50% of the time. So I'd go about to test my hypothesis. I would flip my coin once, and I flip my coin once, and it lands on heads. So now I have results. And I can say from those results that, hey, my hypothesis is correct because this coin does land on heads 100% of the time. And you can see why that's problematic. If I just flip the coin once and it lands on heads, and I say that it lands there, since it landed on heads once, therefore it lands on heads 100% of the time, therefore the coin is rigged, we know intuitively that's not true. And we know that's not true because there's a 50% chance that it's going to land on heads. That's expected. So it could easily been a normal coin and just ended up landing on heads. So the significance I would put on that is, well, 50%. There's a 50% chance that we would see results as extreme as getting heads after one flip. Well, what if I flip the coin again and it landed on heads? Okay, and that is not too far-fetched to say that this coin is rigged because there's a 25% chance that if I flip a coin twice in a row and it lands on heads, then that we would see that happen with a normal coin. So my p-value at that point would then be 0.25. Well, what if I flipped it again and it landed on heads again? Now I got down to now we would say, well, okay, we'd expect that if you flipped a coin 3 times in a row, there's a 12.5% chance that you'd see results as extreme as that. So still plausible. Then if I flipped it again and it landed on heads, we'd be put at 6%, 6 point something percent. Now things start getting suspicious. If I flip a coin 4 times in a row, and I get heads every single time. I flip a coin again, and it lands on heads one more time. That is 5 times in a row that coin landed on heads. If it is a normal coin, there's only a 3% chance that I would see a normal coin land on heads 5 times in a row. And that's where we get statistical significance from. That's what the p-value describes. And we'd say, Well, yes, it is possible that this is a normal coin because we would only see results as extreme as getting heads 5 times in a row. We'd only see that on 3% of the time. It is becomes pretty unlikely that this coin is actually a normal coin. And so that is what p-value represents. Moving on to multivariate analysis. Now there are two different types of main multivariate analysis. There's either explanatory or confounding. Explanatory is just like bivariate analysis. However, instead of looking how one variable affects another variable, you're looking at how multiple variables affect another variable, and you're trying to explain the relationship between a single variable between how you're trying to explain the relationship between how several variables affect a single variable. Now, with confounding analysis, however, confounding analysis isn't necessarily there's not necessarily fixed on a single target variable where it's more looking at how do all the different variables interact with each other. And so I might have a data set and I am not specifically looking for a single variable, how it's affected, but rather I want to know the relationships that all the different variables have. So a common graph when doing explanatory analysis, you start to get a little bit creative with your different variables because you no longer have just two axes. You might add a third axis and make it in 3D like this plot you see over here. You might also add color to represent another variable. You can add size. You can also add triangles or squares or different shapes. And so this is starting to get into how you would convey more complicated multivariate analysis. With confounding analysis, you usually do a pair plots chart like this. And what this chart does is it basically does bivariate analysis for every single variable, and it looks at how every different variable relates with each other, and you can start to see the different distributions that and the relationships that all the different variables have with each other. And finally, it's important to know that all the different analyses build upon each other. Multivariate analysis is made up of bivariate analysis, which is simply made up of univariate analysis. In univariate analysis, I am looking at the spread of this single variable. Well, in bivariate analysis, I'm looking at the spread of that variable compared to the spread of this variable. And in multivariate analysis, I am looking at the spread of this variable and the spread of this variable as compared to the spread of this variable versus this variable, and so forth. So each one builds upon the other, and they all are comprised of one another. And now for this last section, we'll be talking about machine learning. And just like in how statistics was focused on determining causality, now we'll talk about the different methods that can be used to consistently predict outcomes. So there are three basic different types of machine learning algorithms. There's supervised learning, unsupervised learning, and reinforcement learning. And the type of machine learning approach you will take depends on what type of answer you are looking for. Remember, machine learning is all about predicting. So in order to figure out what type of learning you're going to use, you need to know what you are looking to predict. With supervised learning, you use supervised learning when there is a definitive right answer to something. Let's say you can think of this like when you take a multiple choice test, there is a definitive right and wrong answer. So if you were choosing an algorithm to help you do a multiple choice test, you would probably choose a supervised learning algorithm. Now, with unsupervised learning, there is not a definitive correct answer, but rather it's just there's a methodology for being able to go about adding structure to data. Think about like with unsupervised learning, you're given, say, like a group of, or you're given a basket of fruit and you need to organize the fruit somehow. There's not really a specific way to go about organizing the fruit. There's not a correct answer on how to organize it, but it just needs to be organized. You might put different types of fruit together, or you might put them together based on color, or you might put fruit together based on how long it will, when it'll go bad, or if it needs to be refrigerated or not. There's not a specific correct way to do it. It just needs to be organized in some fashion. And finally, reinforcement learning. Now, reinforcement learning is probably what most people think of when they think of AI. Reinforcement learning is where you have an agent that is interacting with an environment. There's not necessarily a right answer, but there is a right strategy to be able to succeed in that environment. Example for a reinforcement use case, if I was trying to play, say, a classic video game like Mario Brothers, where my objective is to get from the left side of the screen to the right side of the screen while avoiding obstacles, I would use a reinforcement learning algorithm for that to determine what action I take at every different time step. Because there's not a right or wrong action, but there's better actions and there's worse actions. The better action is maybe jump over an obstacle rather than walking into it. Or don't walk, you should jump over you should jump when there's an obstacle in front of you versus you should walk right when there's an obstacle in front of you. It's different from supervised learning in the fact that there's not a specific correct answer, but rather it's more trying to determine a policy for going ahead and making choices. So supervised learning, the different types of supervised learning are regression and classification. Some common use cases of supervised learning are image classification, speech recognition, stock price prediction, and sentiment analysis. Um, Whether you use regression or classification depends on the variable type. Unsupervised learning, the main types are clustering and dimension reduction, and the use cases range from anomaly detection to trending topics, factor analysis, or recommendation systems. With reinforcement learning, in and the main types are either model-based or model-free. Basically, what this means is if it's model-based, that means that the agent knows all the different states within an environment. Think about playing chess, for instance. It's very easy for you can tell the agent how to quantize every single different state um, that there is, where model free would be more like something you're teaching a self-driving car how to drive. There really isn't. There's an infinite number of states and you can't model that out. So the agent doesn't actually have the state space with it, but rather is creating its own policies to try to be able to take different actions. And use cases for reinforcement learning is, like we talked about before, um, making AI bots in games, decision making, robotics, and self-driving cars. Okay, so this is the basics of how supervised learning works. So supervised learning will train a model based off of labeled data. So then it can be fed unknown data, and then it will tell you and then we'll give you the results of that unknown data based off the model that was trained off the labeled data. One good way to think about how supervised learning works is it's very much think about trying to teach a toddler. If I was trying to teach a toddler different shapes, I'd have all these shapes and I want my toddler to be able to correctly identify these different shapes. So I might give my toddler a workbook, or I would give them this paper on all this picture over here, and they'd look and say, okay, if you see a shape like this, it's quadrilateral. If you see a shape like this, it's a triangle. If you see a shape like this, it's an ellipse, so on, so on. And so what the computer does is it will look at all this information and then try to train a model based off of this labeled data that it has. Once it's trained its model, then it'll look at unlabeled data and then try to classify it accordingly. However, as you can see, you can also tell though when the model doesn't correctly work. Here I fed it a trapezoid, which is a quadrilateral. However, my model ended up classifying it as a triangle. And you can see that if that classifying this trapezoid as a triangle isn't really that bad of an attempt, because this trapezoid, based off of the labeled data I gave it, does kind of look like a triangle. And if I gave this to a toddler that doesn't know that a triangle only has 3 sides and a quadrilateral has 4 sides, the toddler would probably look and see that, yes, this trapezoid looks most like a triangle, so therefore it's going to call it a triangle rather than calling it a quadrilateral. Another example of supervised learning is, I think that something we're all pretty familiar with, is how um, professors or teachers often give out tests. You'll have a practice test, and then you study this practice test, and after you've taken the practice test, you will then go and take the actual test. Now, the practice test gives you the questions, but it also gives you the answers. It gives you labeled data, and then you train yourself on that practice test. So then when you go into real test, the real test that you will then be able, when you're faced with the unknown data, you'll be able to correctly choose the answers based off of how you trained on the practice test. Now, one thing to know about supervised learning is it is easy to overfit a model. What overfitting means is you train it on so much labeled data that the model becomes very good at predicting the labeled data, but it won't do very good with unknown data. Going back to that example of your teacher giving you a test, this would be basically like if the teacher gives you all the right answers for the test before you take the test, then what a student is going to do is just memorize all the correct answers of the test, and then they're not really learning the subject, but rather they're just learning all the right answers. And they just memorize the right answers. They get 100% on the test. The model performs well, but then when the student goes out into the real world, because they just learned how to take that specific use case of a test, they aren't prepared when faced with unknown data. An example of what that might look like on a graph would be I have a graph that looks like this. I have these different points here. So a normal model would just draw a straight line through there and it doesn't quite get all the right answers, but it gets close. And what an overfitted model, though, would look like would be something like this, where I have all my dots, um, but the line will curve in a way that it perfectly goes through every single dot. And why this is problematic is it won't be very useful for when the model is then exposed to new or unknown data. Usually to combat this, when you do have your known data, you'll usually split it up into a training set and then a test set. So you'll train your model on the training set, and then you'll test it on the known data to see how the model performs, so you know how accurate your model is. Also, with the different types of regression, there's two types. There's classification and regression. With the different types of supervised learning, there's classification and regression. This just depends on whatever your target variable is. If you had a categorical target variable, then you are going to be trying to classify data. You're going to either be putting it based on these characteristics. It either goes over here or it goes over here. It's either a circle or a cross. Where regression is the target variable is a number. So given that it has these inputs, this is going to be the quantitative output that we are looking for. Okay, now unsupervised learning, on the other hand, will take data without any objective labels and then attempt to add meaningful structure to it. So for instance, if this is my data right here, I have all these different shapes. If I'm a unsupervised learning algorithm, I will attempt to add some kind of structure to these shapes. So I'll try to group them. And you can see here, I decided that I'm grouping all these things that look like triangles together. I'm grouping these things that look like rectangles together. I'm grouping these that look like circles together or ellipses together. And then I'm putting the star in its own category because I can't really find another group for it to go into. Now, one thing you want to notice is, look, I didn't say this is my triangle group. I didn't say this is my rectangle group or this is my ellipse group. I just said group 1, group 2, group 3. Because there really isn't, there is no answer or right way how to group these. The algorithm just found some similarities between it and tried to group them accordingly. And there's also not an objective right or wrong answer for how a supervised learning algorithm will go about this. For instance, here's another way that the supervised learning algorithm could have grouped these shapes together. Rather than grouping them based on shapes, it grouped them based on color. But it still says group 1, group 2, group 3 because it doesn't know what color is. It's just noticing they are similar on that type of variable that they have. So that is the basics of how unsupervised learning works. A more practical example than classifying shapes is think about classifying news topics or trending topics. Like you think about Google News, for instance. It doesn't know what topic is the most hot topic out there, but it does see that it can group different types of topics together and know that some topics are more trending than others. When it's going through and classifying different types of user groups, for instance, it will look at, okay, these users all have these types of interests, these users have these types of interests, and these users have these types of interests. Therefore, I'm going to make 3 different groups of users. Then I know that because these users like these types of articles, these users like these types of articles, and they're all similar, therefore I'm going to add structure and group them. But that is the basics of how unsupervised learning works. The biggest key to know difference between unsupervised learning and supervised learning. Supervised learning, there is a definitive right answer. Unsupervised learning, there's not a definitive right answer. Okay, and here are the different types of unsupervised learning. We have clustering and then dimension reduction. Clustering is pretty intuitive. We were just talking about that with grouping different data points together. Dimension reduction is a little bit different. Clustering is focused on groups like data, where dimension reduction is not actually focused on grouping like data, but rather grouping like variables or features together. So where it gets its name, it's reducing the dimensions of a plane of a data set dimensions are features. So I think this is a good visual representation of it. Let's say like I have a scatter plot, a 3D scatter plot that looks like this. You can see though that the way the data is distributed, if I decide to add a new dimension here and a new dimension here, I can plot this data like this. I can reduce it down to 2 dimensions, but still I can capture a lot of the variance in the meaning that this data has. And so the whole point of dimension reduction is trying to boil down variables or group similar variables together. Um, uh, Example I can think of off the top of my head of where you want to do this is you're given a data set of, say, like you're given a housing data set of different housing prices, and you have like your features in that data set. You might have the price of the house, the number of bedrooms, the number of bathrooms, um, and then you have the square feet of the house, but you also have square meters of the house. Um, Now square meters and square feet, they basically will describe the exact same thing. They describe the area of the house, but it's just different proportions, but they describe the exact same data. So what a dimension algorithm would do is it'd look and it'd see that both those variables are similar, and then it would boil those two variables together. So it would either drop square meters or it'd create a new variable that is both square feet and square meters. And it would create a new variable called area. Also, it might look at number of bedrooms and number of bathrooms and realize that that variable represents the number of rooms in a house. So it might also put those two variables together. And this is very useful for data cleaning because when you have too many variables in a data set, it can often ruin a regression analysis if you're looking to do a statistical approach to explain what variables have the greatest impact on your target variable. Like with the house example, if you're trying to predict house price based off of those different variables, what might happen is you will run your regression analysis, and because you have both square feet and square meters, you will see that house prices go up um, by as square feet goes up by 150%, then the house price will also go up by 10%. However, you'll have square meters as square meters goes up by 100 by I'm sorry, by as square meters goes up by 100%, then your house price will drop by 50%. Which doesn't make sense is how can you have square feet going causes your house price to go up, where square meters adds causes your house price to go down if they're really the same thing. The reason is it's just because in the regression equation, it just subtracts it is just subtracting square meters from square feet, and so square feet is much higher than it should be, square meters is much lower, and then the difference between those two is the actual real variance that housing area causes on the effect of how the area of a house causes on the price of a house. Okay, and lastly, reinforcement learning. Now, this is the most common, or this is probably the most complicated form of machine learning, but in my opinion, I also think it's the coolest. And also, just I really believe if you understand how reinforcement learning works, it really helps you understand how we as human beings go about making decisions, as well as I think it really gives you a great insight to AI, and you can start to realize it takes away the black box elements of AI, and I think it can help neutralize any fear that a person may have about an AI because it gives the understanding of how AI works. But with reinforcement learning, there are three critical elements to it. There is an environment, there's an environment. The environment is a place for a reinforcement learning agent to interact with. There's a value function that tells it when it interacts with its environment, whether or not the environment is whether or not it's in a good position or a bad position, and then backward propagation, which is a method for updating the value function to better help the reinforcement learning agent navigate its environment. The main time that you would use a reinforcement learning algorithm is when you have an agent that is interacting within some kind of environment. And it needs to figure out how to properly navigate that environment. For instance, self-driving cars. You can't just tell a self-driving car with a supervised learning approach going forward is good, going back and stopping is bad. A self-driving car is in an environment that's very complicated with multiple states, and it needs a way to know that, okay, it is good to go forward when the light turns green, but it needs to figure out it is bad to go forward when the light is red. It needs to learn that if it crashes, that is bad. You do not want to crash. You do not want to bump into objects. And that's where the real strength of reinforcement learning comes. It helps the agent, in this case a self-driving car, determine on policy for it to be able to navigate its environment. Okay, so I'm not going to go too deep into this. Um, I know I'm also very much so going to oversimplify this, but here is the basic inner workings of how a reinforcement learning algorithm works. So over here is our agent with its algorithm. It is in an environment. What happens is the agent will observe a state that it's in within the environment. It will then process that state through its value function. It will it will try to figure out where it wants to go, and it'll look at the state that it wants to go, and then it is going to take whatever current state it's in and discount the value of that state to determine which next state it should go into based off of the value of the different states. So once it's in the state, it's going to run that state through, it's going to run the different state choices through its value function, and then that value function is going to determine which state it should go to. So then the agent will go ahead, it will take an action, and it will move into that state. When it moves into that state, it will get a reward from that state. It's going to judge the difference in value between the reward that it got from this state and the expected reward it thought it would get from that state. From judging the difference between the reward of that state and its initial expected value of the state, it will then use that, using backward propagation, to go back through its value function and reset all of its weights and biases to better be able to up to create a value function that's more in line with actually achieving what it wants to achieve. I also want to comment, I know I'm using backward propagation, and I know that's specifically used for temporal difference. I am aware of Monte Carlo Monte Carlo tree search algorithms, and I know they're a little bit different, but they both, whether you are using temporal difference or Monte Carlo tree search, they do follow that same kind of methodology of determining some way how to update its value function. So I know this is a very complicated example. I'll try to break this down for you all very quickly with, say, going back to the Mario Brothers example. So let's say like am I'm trying to train I'm trying to train a agent to be able to play Mario Brothers. So what I'm going to do is first, I need the environment, and my environment is going to be a copy of the original Mario Brothers game. And then I'm going to hook my algorithm up to that game so it can see all the different pixels that are being displayed in that game. I'm also going to hook my algorithm, my agent up to the controller for that game so it can control um, it can have inputs in the game. So the pixels or the display of the TV screen will be the way that my agent will observe the different states that it's in, and then it's going to take action through the input of the controller that I give it, and it's going to have the option to either move left, right, press left, right, up or down, jump, or throw a fireball or whatever, and it can perform those different actions. So, and then the next step, now that I have it attached to my environment, I'm going to give it a value function. And the value function, I'm basically going to state it is good when the score goes up. And as your score goes up, that is a good thing. And now, so when it sees the score goes up, then in the environment, it will be rewarded and it will know that it chose a good action because it sees the score going up, and that it will be incentivized to keep the score going up. So now I have that all set out. I will then also have some kind of backward propagation algorithm to be able to judge the difference between what it thought a specific action would lead to and what the actual consequences of that action were. And then it's going to reevaluate its difference between the expectation of a certain action versus how that action actually rewarded it. For instance, it might give the action Mario is moving to the right and there's a Goomba in front of Mario. Goombas are enemies in the Mario Brothers franchise if you're not familiar and you do not want to touch them. So if the avatar ends up bumping into the Goomba, it may have the initial hypothesis that moving right into a Goomba was a good thing. But then when it actually explores that and it bumps into the Goomba, it will notice that its score goes down. So the environment is giving it a reward, and it then realizes that was a bad thing to do by bumping into the Goomba. So it's going to go back and it's going to reevaluate its policy for making decisions, and it's going to change so it now knows that it shouldn't move to the right and bump into a Goomba. It might experiment with jumping over the Goomba or jumping on top of it, and when it jumps over the Goomba and lands on it, it noticed that its score goes up. So now it's going to be incentivized to jump on the Goomba. And so as the agent goes through more and more iterations, it then determines a complex policy that helps it learn how to navigate an environment. Now, one thing I will caution you about if you are trying to set up a reinforcement learning environment is you need to be very careful about how you go about determining what is incentivized and what the value function is. For instance, um, if I tell it that I want its value is determined by the score going up, then the agent's only going to be incentivized by making Mario's score go higher and higher and higher. Now, I might have the objective that I want it to complete the level, but if it's trained on the notion of making its score go higher and higher, it might find an exploit just to continue to get its score to go higher and higher. There's one area on the first level of Mario Brothers where if you jump on a shell that is on a staircase, you can get it in a position where you will just jump up and down for infinity on that shell, and every time you jump on that shell additionally, it will multiply your score by 2. So if the agent learns how to do this exploit, it will be heavily rewarded by doing this exploit because its score will start going up exponentially by doing it. However, it will never actually finish the level. And that's on my problem. That's my fault as the architect of this by not designing a value function or an incentive in a way that actually makes it complete the level. However, if I only incentivize the agent on completing the level, it might never actually figure out how to complete the level just because that task is too complicated for it. It will keep doing random things over and over again, and it can't tell if running into a Goomba or jumping over a Goomba is a positive because it's so far away from actually completing the level, it will never be able to assign value to those actions. So that is really where things get very complicated with training AI, with training a reinforcement learning agent, and it takes a lot of work to be able to figure out. Also, you do not need to know any of this. I'm telling you all of this primarily for your benefit, and this is way deeper than you need to know, but I do feel like it's something interesting to understand, and I think it is important to just have a higher level overview and understanding of how reinforcement learning takes place. And finally, let's tie this all back to strategy and the strategic process. So reinforcement learning, essentially what it is doing, it is following those same principles that we talked about in the previous strategy lecture to be able to determine a strategy for the agent. What a reinforcement learning model does is it tries to take an environment that it's in, it gives it a state space, and then it tries to create value. It has a value function to try to evaluate all the different states within that state space. As the agent moves around, the agent then learns from interacting with its environment. And based off the feedback that the agent gets, in the environment, the reinforcement learning agent will take that feedback to re-update its value policy to change the way that it views the world. So when it all comes down to this, both strategy and machine learning do at its very core break down into these principles of how to evaluate the world around you and looking at the value and looking at the states of the world, what the value of the world is, and to also look at how to take actions over the course of time within that world to be able to achieve the desired outcome that it wants. At its essence, reinforcement learning is really just a method of machine learning for being able to determine a strategy or a policy for an agent to take within an environment, just like the same that a manager might do for a company or any strategist or an agent in whatever situation they may be in. This is why in the previous lecture we took such a computational approach with learning about strategy to see to show how they are both very much related. And just, I believe the more that you learn about the way that artificial intelligence works, if you think about the study of artificial intelligence, you are studying intelligence. And as you study intelligence, you learn you learn more about how beings of intelligence, which we call agents, make decisions. Understanding that process helps you as a being that makes decisions know how you can go about making better decisions. And it's good to have a structured and computational way to think through things. So that is the crossover, how reinforcement learning is related to strategy. Um, And that will be all for this lecture. I hope that you guys enjoyed this, that you found it insightful. I know we covered a lot. We went from the very basics of data to probably some of the most advanced concepts you can get into. Remember, you do not need to know everything in this lecture and understand everything perfectly, but it is good to have a general idea and an overview of how all of this goes together.